Let's look at the amide or amide functional group, and let's start by assigning a steric number to this nitrogen. So the steric number is equal to the number of sigma bonds. So here's a sigma bond, here's a sigma bond, and here's a sigma bond. So 3 sigma bonds plus the number of lone pairs of electrons. So there's one lone pair of electrons on that nitrogen. So I'll go ahead and highlight them there. So 3 plus 1 gives us a total of 4 for the steric number, which means 4 hybrid orbitals, which implies sp3 hybridization for that nitrogen. And from earlier videos, you know that sp3 hybridization means a trigonal pyramidal geometry for that nitrogen. And so that's one way of looking at this functional group, and that lone pair of electrons being localized to that nitrogen. However, now that we know resonance structures, we know that that lone pair of electrons is not localized to that nitrogen. It's delocalized in resonance. So we could take that lone pair of electrons and move it in here to form a pi bond. So that would force us to push some pi electrons off onto this oxygen. So let's go ahead and draw the other resonance structure. So this top oxygen would now have 3 lone pairs of electrons around it and -1 formal charge. And there'd be a double bond between this carbon and this nitrogen. So let's go ahead and draw in everything. This nitrogen now has a +1 formal charge, and we can go ahead and complete our resonance bracket here. So let's follow those electrons along. The electrons in magenta, the lone pair of electrons, moved in here to form our pi bond. And the pi electrons over here, right, in blue, came off onto the oxygen to give the oxygen a -1 formal charge. All right, let's now calculate a steric number for this nitrogen in our second resonance structure here. So steric number is equal to number of sigma bonds. So here's a sigma bond, here's a sigma bond. And our double bond, we know one of them is a sigma bond and one of them is a pi bond. So we have a total of 3 sigma bonds around our nitrogen. 0 lone pairs of electrons, so 3 plus 0 gives us a steric number of 3. That implies 3 hybrid orbitals, which means sp2 hybridization, and a trigonal planar geometry around that nitrogen. So a planar geometry. And here we've shown our electrons being delocalized. So the lone pair of electrons are delocalized due to resonance. And so experimental studies have shown that the amide functional group is planar, right? So these atoms actually are planar here, which means that the electrons in magenta are not localized to that nitrogen. They are actually delocalized. And so that implies this nitrogen is sp2 hybridized and has a p orbital, and that allows that lone pair of electrons in magenta to be delocalized. And so here's a situation where drawing resonance structure helps clue us into what's actually happening. That lone pair is participating in resonance, which makes this nitrogen sp2 hybridized, so it has a p orbital. All right, let's look at this example down here. All right, and let's look first at this left side of the molecule. And so we can see our amide functional group. And if I look at the lone pair of electrons on this nitrogen, we've just talked about the fact that this lone pair of electrons is actually delocalized. So this lone pair is participating in resonance. And so that, of course, affects the geometry and how you think about the hybridization of this nitrogen here. So the electrons in magenta are delocalized because they participate in resonance. And if I think about, let's make this a different color here. Let's make these electrons in here blue. So the electrons in blue on the amine, right? These electrons have nowhere to go. They can't participate in resonance. That lone pair of electrons in blue is localized to that nitrogen. And so this is why you can think about an amide being different from an amine in terms of functional group and in terms of how they react and how they behave. If we look at another example, so this molecule right here, and we assume the lone pair of electrons on that nitrogen is localized to that nitrogen, let's go ahead and calculate the steric number. So the steric number would be equal to sigma bonds, so that's 1, 2, and 3. So 3 sigma bonds plus lone pairs of electrons. There's 1 lone pair of electrons on that nitrogen, so 3 plus 1 is 4. So 4 hybrid orbitals, which implies sp3 hybridization on that nitrogen. But we know that that lone pair of electrons is not localized to that nitrogen. That lone pair of electrons is delocalized. It participates in resonance because we have this pattern here, right? So this pattern of a lone pair of electrons in blue, right, next to a pi bond, which I will make magenta right here. And so we could draw a resonance structure. So I could take the electrons in blue, move them into here, too many bonds to this carbon, so I push the electrons in magenta off onto this carbon. So we draw the resonance structure. Right, so I have my ring here. The nitrogen's bonded to a hydrogen. The electrons in blue moved in to form a pi bond, and the electrons in magenta moved off onto this carbon right here to give that carbon a -1 formal charge. All right, let's go ahead and calculate a steric number for the nitrogen here, which gets a +1 formal charge. All right, so the steric number will be equal to number of sigma bonds. So there's 1 sigma bond, here's another sigma bond, and then in our double bond, one of them is a sigma and one of them is a pi. So I'm saying that's our sigma bond. So the steric number is equal to 3 plus the number of lone pairs of electrons, now 0. So that's a steric number of 3, which implies 3 hybrid orbitals, which says sp2 hybridization. And since we know that that lone pair is delocalized, right, it's going to occupy a p orbital, and so therefore this nitrogen is sp2 hybridized because we know sp2 hybridization has 3 sp2 hybrid orbitals and 1 p orbital. So that lone pair in blue is actually delocalized. It's occupying a p orbital. And so let's go ahead and draw that down here. So let's say this is the nitrogen, and you're looking at it at a bit of an angle. If that nitrogen is sp2 hybridized, that nitrogen has a p orbital, and so we can go ahead and draw in a p orbital on that nitrogen. And so the electrons in blue, right, since those electrons are delocalized, those electrons are going to occupy that p orbital. Those electrons can participate in resonance. All right, so let's go ahead and draw a hydrogen in here just to finish that off. And I could have kept on going with resonance structures, right? So I actually forgot to put in these electrons right here because I could have kept on going. I could take these electrons in magenta, move them into here, and then push these electrons off onto that carbon, and I could keep on going. And so there are many more resonance structures that you could draw. I'm not going to do so for time purposes. Here I'm just trying to show how resonance affects the hybridization, or how you should think about the hybridization when you're drawing these imperfect dot structures. Let's go ahead and finish our picture of the molecule because we know that these 4 carbons here, right, all have a double bond to them. And so those 4 carbons are therefore sp2 hybridized. And if those carbons are sp2 hybridized, right, each one of those carbons has a p orbital. So I could draw in a p orbital on all of my carbons here. And you could think about those electrons. Let me go ahead and highlight them. The electrons in red here. So these pi electrons, right? So those pi electrons are participating in resonance. And so we have a total of 6 pi electrons participating in resonance. Those 4 in red that I just highlighted here, and then these electrons here in blue, which occupy this p orbital. And so this is going to be extremely important when you talk about aromatic compounds later in the year. So for right now, just try to identify the skill of delocalized electrons versus localized. In this case, the electrons on the nitrogen are delocalized. They participate in resonance. Let's do one more example, so one final example here. All right, and let's go ahead and start by calculating the steric number of this nitrogen. So how I've drawn it here. So steric number is equal to number of sigma bonds. So here's a sigma bond. I have a double bond. One of them is a sigma bond. So I have 2 sigma bonds plus lone pairs of electrons, right? There's 1 lone pair of electrons here on this nitrogen. So 2 plus 1 gives me a steric number of 3. That implies 3 hybrid orbitals, or sp2 hybridization. So if that nitrogen is sp2 hybridized, that nitrogen is going to have a p orbital. So let me go ahead and sketch in a p orbital here on this nitrogen. And let's think about the other carbons too. So let's think about these carbons, I should say. So I have 1, 2, 3, 4, 5 carbons. All of these carbons have a double bond to them, so all of those carbons are sp2 hybridized. So I can draw in a p orbital on all of those carbons. So all of those carbons have 3 sp2 hybrid orbitals and a 1 unhybridized p orbital. So it's the same idea with this nitrogen here. If this nitrogen's sp2 hybridized, it has 3 sp2 hybrid orbitals and 1 unhybridized p orbital. I already drew in the unhybridized p orbital. Let's go ahead and put in those sp2 hybrid orbitals, and I'll use magenta. So one of those sp2 hybrid orbitals is forming this sigma bond over here, another one's forming this sigma bond back here, and then the third sp2 hybrid orbital must be here. And that's actually where that lone pair of electrons is, right? So this lone pair of electrons here in blue is localized to this sp2 hybrid orbital. So this is actually, let me go ahead and draw an arrow here. So the lone pair of electrons is actually localized to that sp2 hybrid orbital. So that lone pair of electrons can't participate in resonance because that nitrogen already has a pi bond, right? So if I go over to here, right, these pi electrons are using that p orbital, and since those pi electrons in green are using this p orbital over here on the right, so this p orbital over here, that means that those electrons in blue can't use it, and so therefore those electrons in blue are actually localized to that nitrogen, which might not be what you first thought, because we talked about the pattern, of course, of the electrons in blue here, lone pair of electrons next to a pi bond. So you might think we could draw a resonance structure. However, the reason we can't is, once again, those electrons in green, right, are actually participating in resonance, and so they're already using that p orbital. All right, so this is kind of an exception to what we talked about before, where we said if there's a lone pair of electrons next to a pi bond, that lone pair is delocalized. So this is the one thing to think about.